we saw paper award as well as student demo. And he have received a lot of like award from IEEE as well as the society from the industry sectors. So without saying too much, let's give the floor to Professor Mi on his great talk on the EV.
Thank you for the round of applause. That's great. Thank you, Japan, for inviting me here to share my recent research with all of you. I heard from Professor that you guys are all graduate students, like undergrad, masters or PhD. Some, okay, yeah, okay, great. So in today's presentation, I will talk to you about the electrical vertical takeoff landing airplane. That kind of research we have done already this year for 4 years. So from this program, we produced one PhD. Looking for a job right now. Okay, so let's see. What? Maybe I know. Maybe I have to click. So if you give me 1 second, I'm gonna go back. Okay, so that's the title. And if you look back at airplane, we have a lot of advancement in the past like 100 years. But of course, the most progress was made in the early 1900s, when we have the Wright brothers invented the first airplane flying for 30 seconds, and then later on we move on to propeller airplanes, and then we have jets, and then now we have like, supersonic fighters and all kinds of airplanes. But if you look at the manufacturers, there are really only 2 manufacturers in the world right now. So one is Airbus, the other one is Boeing. So they make commercial airplanes and also military airplanes. You have like some smaller airplanes, like a Cambodia, they make smaller jets. There are also some new airlines, new airplane manufacturers emerging, but it's going to take them some time to be really to take the market share, like there's one in China, the C919, there's one in India. So they're doing some great work. But if you look at the airplane industry overall, we have a few like issues we might actually not notice. So one of the issues is emissions. You might not know that per passenger per mile basis, airplane emits more than the electric car. So that's one of the things that because air transportation become more and more popular. So it seems that the emission, even though right now, air traffic emission counts very little in terms of total CO2 emissions, but over time, this is going to increase like double digits every year. So therefore, it's going to become more significant in the near future. And the other aspect of airplane emission is that most of the emissions happen like in the air, which has more impact in terms of global climate change than the ones that are on ground. It takes time for those things to travel to certain places, and it's global. And it's not just emits in the US, it's impact US, but actually it moves with the atmosphere to different places. So with all that in mind, so there have been talks about transferring airplanes to more sustainable. The ways to do that, including like a sustainable air fuel, which instead of using jet fuel, you produce fuel from food waste, things like that. But then more talk is that can we do electric? If we can do electric, of course, if we can produce electricity from your renewable energies, and then we'll be solving this emission problem. Right? But the idea is that if you look at one of the airplanes as an example, now I took the largest airplane, 747, probably not the largest, but kind of one of the largest airplanes. And if you look at the fuel consumption, it takes about 56, equivalent to 56 miles per gallon per passenger, right? So that's what I'm saying. It's probably worse than a passenger car. I mean, for a passenger car, you take 2 or 3 people in a passenger car will be much less than that. But if you look at the total energy consumption, it's 2.5 gigawatt hour for the airplane to fly one way, for its whole distance, like from say Los Angeles to Shanghai, flying one full flight. It takes 2.4 gigawatt hour. That's a lot of power because a lot of the power plants only generate a gigawatt hour power, and it takes about an hour to generate the whole electricity needed for flying one run, right? Of course, generation is actually not a problem. The problem is that the total weight, because if we need 2.4 gigawatt hour, you transfer that weight, that energy into weight. How much is going to weigh? It's about 6 million kilograms, or 6,000 tons of weight. You might not have an idea how much is that 6 tons. I mean 6,000 tons, not 6 tons. 6,000 tons. Okay, think about the truck, like the 18-wheeler, like a really long truck. It carries about 50 tons. The smaller truck, like F-150, it carries about 1 to 2 tons at the most. 6,000. It's like 3,000 to 4,000 F-150s. That's kind of ridiculous, right? It's too much weight. And plus, if you look at the airfreight, the airplane, a Boeing 747 is only 412,000 kilograms. So if you take this number divided by that, that's almost like more than 15 times the weight. The problem, of course, is that when we calculate the energy needed to fly the airplane, we didn't consider this weight. If you put this weight on the airplane, it would need not 2.4, maybe 10, maybe 20 kilowatt hour, and then you have an increased weight. So ideally, you will not have an opportunity to fly airplane from Los Angeles to Shanghai with batteries, because every time you put more energy, you increase weight. And you create need more batteries. Eventually, it will be a giant that you will never be able to fly. Okay, so that's the bottom line: is that is not likely to happen with the current battery technology. But we have been increasingly to use more electrical power in airplanes. Those you can consider a lot of the entertainment system, de-icing, also maybe a lot of flight control, things like that. They're more electric, but they're not electric airplanes. So that concept is called like more electrical airplanes. We're doing more electric than we used to do, say, 10 years ago, 20 years ago. We're doing more. When we do more electric, we need more electricity. And that electricity right now is generated from the gas turbine. The gas turbine drives the electric generator, and the electric generator produces all the electricity you need. And also you have an onboard battery to supply power when the engine is not working or working at extremely low speed. So you have a lot of this electric equipment. You have generator, and then you have battery. The Boeing 787 is the first one to put a lithium-ion battery on it, and also the first airplane that had the issue with the battery being on fire, and they have to address the issue for some time. So by doing more electric, really, it just helping to make the airplane like in terms of weight, for example, it reduces hydraulic, so it reduces weight, and also in terms of flexibility, it helps with the control. So therefore, we kind of improve the performance, convenience, and reliability, a lot of aspects of airplane, but not electric airplanes. Because we talk about the weight of the battery is not possible for to build a pure electric airplane at this time. So the IS has been focusing on smaller airplanes, and particularly on the electrical takeoff and vertical landing airplanes. The reason is that this electrical eVTOL aircraft, they are small. They don't need runway to take off. So you can take off from, say, a backyard, or you can take off from a roof of a hospital, and you can land in any place where, say, you have a rescue you have a disaster area that you can do rescue. You don't need a runway to go. So the function is very similar to helicopter. Right? So this is good. For example, urban transportation. For example, we have nowadays. For example, you have a helicopter to transport the president from the White House to Air Force One. So that's done by helicopter. And we have celebrities in the Beverly Hills area. They go to work somewhere else or play golf, and they don't want to be in congestion, so they take a helicopter to somewhere and then save them time, right? But so you might ask, okay, we got helicopters, why do we need those? There are a couple of things you can think. One is that this eVTOL is much quieter. Helicopter is very noisy. The helicopter with the blades is very noisy, and the speed of helicopter is slower than eVTOL. eVTOL can fly much faster, and the takeoff also actually faster, and it flies faster, and it's less noise, potentially more reliable. Because the helicopter only has one rotor, and if that rotor something happened like a couple of days ago in Honolulu, the blades got somehow detached, and then the whole airplane was down to the river, and everybody was killed. But with the eVTOL, you typically have multiple propellers. So one of the propellers is dead. It's okay. Even half of the propellers are dead, you will be still to survive the airplane. So reliability-wise, safety-wise, it definitely is going to be better. So that's why it takes a lot of interest from the general public saying, well, let's do it. But the problem that we have today is that we need a battery. Even with the eVTOL, the battery energy density is too low. The battery is too big. If you got a 600 kilograms of battery, enough to fly for like 30 minutes. Now, if we reduce the battery weight to 150, let's say, you can ride like 4 more people in an airplane. So basically, it's a weight. And the cost is one of the issues. Batteries are still expensive. The unit price is not bad, but think about this battery only lasts for 1,500 cycles. If the airplane flies, let's say every charge you fly once, and you fly say 5-6 times or 16 times a day, you can only fly 100 days. The battery will be like no good. They have to replace the battery, right? So that perspective is expensive. And so we have a project with DOE on developing this new battery that can reach 1 kilowatt-hour per kilogram, which is 4 times better than what we have today. The best lithium battery today can produce, the commercial ones can produce 250 watt-hour per kilogram. So we're doing this one. So hopefully this, we are one of the recipients. There are totally 11 recipients. Everybody's working on developing battery that can do better for eVTOLs. But when you get down to the eVTOL study itself, it is truly a multidisciplinary subject. I mean, you look at electric vehicle, it's a multidisciplinary, but if you look at eVTOL, it's even more multidisciplinary. Think about like the design involves a lot of the aerodynamics, mechanical aspect. Then you have all the like safety, reliability issues, electrical issues, thermal issues, and materials, things like that. So it's not multidisciplinary domain, and we are basically looking at how can somebody or some company to design a eVTOL with the existing knowledge we have, because there's nothing really available. Right? You're designing from scratch. The traditional airplane design, it doesn't apply to here. The traditional electric vehicle design, some of them might apply, but some of them not. So we have to see how we can design them together. So this is one of the main subjects that we work with UCSD and a few other universities together and the companies on a NASA University Leadership Grant to design a platform. But with this platform, anybody can go in to input the parameters like the distance, the speed, the payload, and then the software package will produce the initial design of a eVTOL, such as the size, the wing size, the body weight, airframe weight, the battery size, and the power needs, the number of blades, the speed, and all kinds of will come out. And from there, you can do further optimization using the program itself, or you can do your own like in-house optimization of the eVTOL design. So that's what we did. And you look at the interest around the world, it's tremendous. I listed just a few here. There are more than like 20 either manned or unmanned electrical aircraft, and 3 of them are actually commercially available. You can purchase. You can put a purchase order. They will deliver that to you in a couple of months or a couple of years, depending on which company you're working with. And then some of them using like multiple blades, like one like this one single person, and some ones can sit 4 to 6 people, and then ones that actually sit 19 people. I know like the 90 airline has booked more than like 100 such airplanes, because there's need for that. Of course, I want to be cautious in that this thing is still expensive, it's still early stage, and it's not for everybody. Why I go to places and people know that I do this, they ask me, okay, why can I buy one that I can drive to work? I said, no, that's not going to happen, because this, if everybody drives a eVTOL, I mean, it's not safe for sure. Right? I mean, we got automobiles on the road. There's so many, and we know that it's already congestion, and there's always a safety concerns. Right? So this like companies 2025, early 2025, you can see some of them can travel 300 miles, some of them like 16 miles. Some of them 1 person, some of them 2 people, 4 people, 6 people, and so on. In fact, the earliest one was designed by NASA as a demonstration project, and this one can fly 100 miles at a speed of 172 miles per hour. It uses 14 electric motors, some of them for like core, some of them for like a cruise. Okay, so this kind of becoming the model for eVTOL design as like a baseline. If you want to design something, you can use that as a base model to compare. But when we say that electrical is not likely possible, so nowadays we're talking about hybrid. Okay, so hybrid may be a possibility in the middle term, and maybe in the long run, when we have a better battery, even the one with 1 kilowatt hour per kilogram, it's still not likely to be for long haul airplanes. Maybe good for eVTOL to increase range from say 30 minutes to say 2 hours, or maybe from payload for people to maybe 10 people or 20 people, but still not good enough. Let's say from flying from Los Angeles to New York, it's not likely because it's going to too much weight on the airplane. So in the immediate time, it's likely that we might see hybrid airplanes to be existing, just like electric vehicles. From the 1960s, people have been designing that, having prototype, selling a few, like the 90s, we are selling UV1 and so on, but then it comes and goes until only the past 10 years, UV has started to be fully commercialized, and then people can go and buy one. So we talk about the difference between different topologies of electric airplanes. You can have, say, the pure electric. You might have like a battery, and you the architecture provides. You might know that DC-DC might not need it. It depends on the design philosophy, because adding DC-DC is going to add cost to the system and weight, but it gives you flexibility of the system and also increase the performance of the system. And the reason I said performance, I'll give you one example. Typical battery has a wide voltage range. A single cell can change from 2.5 volts to 4.2 volts. That's a big change. So when you build a battery in a pack, the voltage can change. Let's say for 400 volts battery pack on the UV, it can change from 250 volts to 420 volts. For that wide voltage range, if you want to control the blades at a constant speed in a different voltage range, you have to use some sort of, say, flux weakening or some other method. So it becomes more difficult to maintain the power, torque, and the speed of your motor. If you have DC-DC, you can potentially maintain a constant DC bus voltage regardless of the input voltage. And therefore, your inverter to control the motor will become so easy, you don't have to worry about a lot of control variables, and your performance of the eVTOL will be much better. So this is just kind of one of the architecture with pure electric. Again, as I said, you can potentially remove, but including that will give you some benefits. In your design, we will have to evaluate. Do we want a DC-DC to get the performance, or do we want to get rid of the DC but reduce the cost? That's the trade-off, right? So you probably have to do optimization scenario. And then also there is a trend to look at fuel cells, because if a battery doesn't work the way that we wanted, we can potentially use fuel cell, because fuel cell using hydrogen. Now, how to produce hydrogen is a different story, but at least you have hydrogen. We can carry hydrogen, which is much lighter than the battery, and then we can potentially fly airplane with a fuel cell. And in fuel cell, you definitely need a DC-DC fuel cell cannot sustain a high dynamic load. Therefore, you would have batteries, because again, battery is going to supply the high power dynamic performance of the system. So this is what you have with your high fuel cell airplane. It's similar to battery, but just that you would have battery pack connect to the DC bus. And then if you look at fuel cell, it's kind of generating electricity from hydrogen, and then you have a motor to drive the propellers. So therefore, if you replace the fuel cell with the engine, you will have simply a series hybrid, where you have an engine to drive a generator. So this two in a fuel cell will be a fuel cell unit, right? And then of course, you would have to rectify the power from the generator and then provide power to the inverter, drive the motor, drive the propeller. With a series hybrid, typically we have a smaller engine, and then we have battery to supply the peak power. But of course, in an airplane, the engine size has to be such that you will be able to do the cruising of the vehicle for whatever conditions that you might encounter. The only thing that is the battery would supply power in a kind of turbulation or in like a in the takeoff period, you need more power, and this comes in to provide more power. Airplane. And then there is also, so if you look at the previous diagram, we have a battery over here and a DC-DC to manage the DC bus. But if you remove that, this will become what's so-called a turbo electric, which means they don't have a battery. Of course, they might have a battery for the auxiliary power, but they don't have a battery for the propulsion system. If we remove that, it becomes turbo electric. So directly, you have engine provide power to the generator, rectify inverter, and so on. So in this case, the advantage is that you have a better propulsion performance, but the disadvantage is that instead of using the engine mechanically driving the propeller, you have to have like two stages of power transfer. So the efficiency may not be the best. So when people talk about this with other advantages, then you might use. Also, we could build a parallel hybrid, because with series hybrid, apparently, or with turbo electric, the engine has to be sized such that it provides all the power you need. But in a parallel hybrid, what we're doing is, instead of being the series connection, we have a mechanical coupling device where engine coming in and we have a motor coming in, and their mechanical power is added as a mechanical coupling. And because mechanical coupling is designed such that you can either add the power of the engine and motor, or you can split the engine power of the engine so that you can use motor as generator to charge the battery. And this is very popular in electric vehicle application, because where we have like city driving, stop and go situations where you use battery only when the power is small, and then you use both engine and motor when you accelerate to cruising, you use engine only, so there's no push stage of power conversion. But in the airplane, this doesn't seem to give you that kind of advantage, because once you're in the air, your flight basically is kind of constant speed, constant power. So therefore, that mechanical power device apparently probably this motor is either like not doing anything, or it might just generate the power for your auxiliary power supply. So it doesn't provide you with a lot of advantage, but still, from an academic point of view, it's worth to investigate what kind of advantage you will get, what kind of cost, what kind of performance enhancement you will get from this design. So, and then that previous one is basically a parallel hybrid, but similar to electric vehicle, we can potentially design series parallel, which means like we have potentially an engine driving mechanical coupling and with a motor driving as well. So you can do the mechanical coupling. And then you have a generator, which is from the engine out power to generate electricity. So with this motor and generator, what you're doing is you can balance the operation of the engine such that you will get the best efficiency out of this whole system. And this is particularly important in electrical or hybrid electric vehicle design, like the Toyota Prius is a typical model of this. Because the city driving, so the fuel efficiency is significantly improved. But in airplane, again, this model might not give you all the advantage you have in electric vehicle because airplane tend to be running at a constant speed and constant power. Right? But again, this kind of one of the potential opportunity that you might want to look into. In terms of propeller design, most of the airplanes today, the electric airplane, like traditional airplanes, most airplanes we have 2 engines, right? 1 on each way, and the 747 of course has 4 engines, and those engines look like they're balancing like the force, right? But actually they also give you the redundancy. If one engine fails, the other engine would still work. With the pilot, they just have to maneuver the airplane in a way that it will balance the airplane. So it's good, but still we have airplanes sometimes. It just happens that both engines fail, then you have a fatal accident. You might be able to mount multiple engines, but it's just not economical. Not easy to do that in the traditional jets. In electric airplanes, apparently it's beneficial to do multiple propellers or multiple engines. The reason that the small motors are more reliable and easy to make, and it's also the weight and cooling, everything becomes much simpler to do. But the other thing, of course, is redundancy. When you have multiple propellers, really 1 or 2 of them fail, it's not a problem, and it's really much safer with this design. So most of the eVTOLs, even though it's like very small power, but you still see them have like 4, 6, 8, even something 10 to 12, 14 propellers. Okay. And also the other thing that in the eVTOL, you have takeoff period and also you have cruising period. So in the takeoff period, the power demand is different from the cruising. So often these eVTOLs have different motors. So say 2 motors for takeoff, and then you have propellers that for the cruising, so they use different motors because they're running at like different speeds, things like that. Now, of course, you can interchange these motors if you have an issue with a system failure, so that further increase your system reliability. So as I said before, our problem today, or anybody's problem today with electric vehicle, is the battery. And battery, you can name many of their problems. And the most problem is the low power, low energy density, and cost, of course, is the issue. And the cost in airplane is different from electric vehicle, different because the cycle life is a more problem. In the E-way, you buy one because the weight that you drive your vehicle, you can drive like 10 years, no problem. But with airplanes, with the current battery cycle life, you can drive maybe 100 days, 200 days. And that's a huge difference. So we're developing better batteries, okay? And also I have been working with some colleagues earlier to look at nuclear batteries to see whether they can provide the power and energy we need. Now, nuclear battery is not actually a nuclear reactor; it's a nuclear radiation, which means this system is relatively safe. The nuclear reactor, if they fail, they explode. Okay, so if this system fails, it just emits radiation, so it's not going to explode, right? So that's a good thing about this one. Now, of course, it fails the emission, but we have this shielding, so the emission it won't go much beyond the shielding. So this system is 100% safe. so you don't have to worry about nuclear. The only thing that is how long you can use this system, eventually how do you recycle it. So, and the half-life, at the end of the half-life, we have to recycle them somehow. But it's better than the nuclear reactors because this radiation, it becomes low and low and low, and eventually it can be just disposed. By nuclear reactors, when they retire, they still have a lot of radiation. It takes about 30,000 years for the radiation to totally go away, okay? But anyway, the energy density is very high. It can go up to 400 to 800 kilowatt hour per kilogram. But the problem is a lot of power. So every kilogram, it reduces like watts, maybe less than watts. So which means you put a lot of weight, you got enough energy to drive it, but you don't have enough power. So if you don't put enough power, the weight is going to be too much that your vehicle, your airplane, again, will not take off. Okay. So we have a problem. And we look at a few like design examples. The previous example I gave you was a large airplane, probably one of the largest airplane, and also for the probably one of the longest distance, about 8,000 miles. But I know 747 can fly nowadays well beyond 10,000 miles. But then we look at this little like intermediate airplane, not long haul, but not international flights, but domestic long haul airplane. Again, like from Los Angeles to Maine or to Boston, for example, right? So we took this airplane and we found some parameter. We want to see if we want to cover this airplane, what kind of battery we need, so that at least the battery people have a target. Okay, we're going to work towards that goal. Maybe not now, maybe 5 years, maybe 10 years, maybe 20 years, or maybe even 50 years, right? So we can realize that goal. We can fly pure electric airplanes. There's a lot of data on this one, but the highlight of this, the range is 5,600 kilograms from San Diego to Detroit, and the total weight is 79,000 kilograms, and the payload is 14,000 kilograms. The fuel capacity is 20,000 kilograms. So this is something that even many years ago, I didn't understand. Like the fuel weight is more than the airplane weight. And then that's an interesting part, that you take so much fuel on the airplane to take off. And okay, so airplane mass is 41,000, and then the fuel pump and so on. And eventually, the passenger is 96 miles per gallon. So based on all these numbers, we're doing this like a estimation saying, if we want to do this, and we have how much energy do we need? We found that by all this calculation, the total energy we need is 18 megawatt hour energy to fly that airplane. That's the total energy needed, including that 1.2% reserve. What happens is you can't have exact the same, because if something happens, the weather changes, you will be able to fly to a nearby airport to land, right? So typically they want you to have at least 20% reserve. Even with traditional airplane, you don't need that too, okay? So 180 megawatt hour. And if our battery from today, 250, we get to 400, which this number is already realized in laboratories. It's not commercialized, but it's in laboratory. So given that battery, how much weight we were going to need for the battery instead of jet fuel? And we found that the battery mass is going to be 356,000 kilograms. And 350, how much is that? Again, you have to understand, the airframe is only 41,000, which is less than, like almost, what? 90, like 9 times. 9 times this battery is 9 times of airframe. The payload is only like 16,000 kilograms, right? So anyway, this is 360, so that's like more than how many times? 20 times. Yeah. So this one means that it's not possible even to drive airplane from San Diego to Detroit. Okay. So now if we want the airplane, let's say, to carry this, let me go back to one slide, you can see. If we say we want to carry the same weight of jet fuel as a battery, what kind of battery energy capacity you would have to achieve in order to get that? So we found that. We want to do that, we need this to get in 14.3 kilowatt per kilograms. The best battery in the laboratory we have today is 400, so 0.4. 0.4. So we need to increase energy density by like more than 30 times, more than almost 40 times, 35 times to get what we need in, say, a couple of years or many years to come. So then we also did, because we have some inquiry from shipyard, and they said, oh, can we do like ships? The airplanes have to carry weight, but ships, no problem, we can carry weight. Okay, then we said, this we did two examples, one is from Japan to Los Angeles, again, the ship, and we found some of the interesting information, like range, weight, fuel consumption, speed, and things like that. So we did, and then we found that the fuel that we need, like 3.5 gigawatt hour for this ship to travel within for that kind of distance. Again, this also includes 20% of reserve time. So if we want to carry a battery at 400 watts per kilograms, and then how much weight of the battery is 10 tons? No, 10,000 tons of battery. And remember how much ton is weight of the, we have that? Or the tonnage, yeah, it has 34,000 tons. So which means this is almost 1/3 of the cargo ship weight. Do you want to sell this to a cargo shipper? Then they really like it. Oh, because if I can carry 10 tons of goods, I can earn a lot of more money than carrying battery around. Okay, and so then what if we carry the same weight as the fuel, and we achieve the same distance, how much like energy density we need? It turned out to be like 11.1 kilowatt hour. The airplane was 14, so not so much difference, really. So so this is the like the fact that you have. So then we'll talk about this company about, can we build a hybrid? You can build a hybrid, potentially we don't need that much of battery. We can put some batteries and we still have the engine with the battery. If we can reduce the size of the engine, then we can potentially save some money, and we use that money to build this electrical motor and battery, right? So we can get the efficiency better. You will still be saving money because the efficiency is better. So this is the architecture that between like with a parallel hybrid and with the engine, and then you have electrical motor, you drive the powertrain. Okay, and well, it turned out that yes, ideally this would work similar again to electric vehicle, but the problem is for ship, for 14 days of travel time, 12 days, they're traveling constant speed. They're not changing. So adding this extra system there doesn't do anything for 14 days. Only at the beginning, maybe when it's dark, when it's slowing down, you can generate some electricity by doing the regeneration. Right? So we have an issue. But anyway, again, so this is not the dead end yet. So we'll talk about looking at we'll do some modeling. It's not possible to build a ship in my laboratory, but we'll do some modeling to see, to emulate the real operating and to see if we can get actually some benefits. If the benefit is going to help over long run to save money or improve the environment and reduce emissions, things like that. But when we did that, we certainly want to say, okay, so we need to put the engine and motor to work together. How do we make them work together? we need to do the mechanical coupling. Remember earlier I talked about the parallel hybrids and things like that. So in the mechanical coupling, ideally we can do either torque coupling or speed coupling. In the torque coupling, basically we add the motor torque and the engine torque to get the total torque. And when we add the torque, the speed of these two systems are proportional to each other. And this K1 and K2 are the speed ratios or gear ratios. When you do the speed coupling, the torque coupling, you can do, for example, gear. You have two input gears, one output gear. Okay. And you can use pulley, like two input pulleys and one output pulley. The same thing, just reduce one. But also, most notably, you can do this on one shaft, which means you mount this motor on the output shaft of the engine, between the engine and the propeller, so you have this motor in the middle. And the motor can be running like as a motor, or it can run generator, take power from the engine, or it can just freewheel. Like if you don't operate the motor, that's okay too, right? So this, of course, in the ship, the motor was like, how that big, like a couple meters tall. So adding that motor in the middle, having that shaft, it's mechanically, it's just such a difficult thing to do. But that's more like a mechanical engineer's problem, not my problem. I can design the motor. And then in addition to the torque coupling, we can also do speed coupling. So in the speed coupling, we basically add the speed. And then when we add speed, the torque are proportional. So K1, K2 are the torque ratios. And you might say, okay, why do you add speed? Well, at the end of the day, what is the power? And power is torque times speed, right? So if the torque is the same, but speed is increased, you would increase the power. So torque times speed gives you extra power. All you need at the end of the day is how much power. Torque is important, but torque is only important when, let's say, you're starting the system when you're zero speed, you don't have power, but you still need torque, right? But at normal operation, speed is important. How do you do speed coupling? How do you add speed? So the most famous method is to use gears to use a planetary gear. With a planetary gear, you have a sun gear, then you have this ring gear, and you have carrier to output, and the ring gear inside, the sun gear inside and ring gear outside, the speed is added. And then the torque is proportional to each other when they're rotating. You can also block one of the gears. You block the ring gear, for example, you only transmit it from the sun gear to the ring gear, to the carrier. And you block the sun gear, you have ring gear transfer. So this is very easy system. Of course, for small power, it's easy, but for high power, such as the electrical ship, it's very difficult to do. And then you have other topologies you can do. So a copper shaft is one actually I think might have, if we can resolve the mechanical issues like the torso and all the balancing and all that stuff. But luckily there are no speed generally, so it's not bad. And we can potentially address a lot of issues with the motor. You have input engine connect here, you have propeller connect on this side. So that is probably one of the best ways to do it. So in a nutshell, electrical airplanes and ships are not even available for even like middle-sized and medium distance. But small, like short range eVTOLs are potentially something that we're going to see a huge progress in the next couple of years because we already have commercial ones available. There, of course, a lot of research needs to be done to optimize the system design, things like that. And the battery needs significant work in the next few decades, I would say, in order to have pure electrical airplanes and ships. And then in the meantime, we need to study whether parallel series or any hybrid structures or even fuel cells would make sense to build airplanes and ships. Because they may or may not, we don't know. On the concept, you see there's some advantage, but there's certain things that are not ideal. So we need a lot of research to do, to get to that point. Maybe I have a few more minutes. I just give you a brief overview of how the research we've been doing at San Diego State. Now, for some of you, if you don't know San Diego, probably how you know San Diego is only an hour, 2 hours, 3 hours actually. So traveling 3 hours from here. So we are a very nice city. Um, in my research group, we have some research in wireless charging. We focus mostly on high power stuff like kilowatts EV charging. We have some publication in the past on low power things, but not much. And we also do a lot of work in battery management systems. We originally are working on this wireless BMS. Yeah. Oh, sorry. Yeah. So we're doing something on the wireless BMS, trying to eliminate the connections and soldering points to increase the system reliability. And we earlier I mentioned about this ARPA-E funding project to develop a new battery that can achieve higher energy density to be much higher. And yeah, so this one is a lithium air battery. We already achieved 1 kilowatt hour per kilograms, but still not good enough. Another project funded by National Science Foundation was looking at the cybersecurity, because with all the power electronics in our system, like EV charging, like renewable energy, and so on, there's a lot of potential that people can hijack the controller of the motors and inject the fake signal, so that your system will be seeing a huge problem that can trigger a fault and your system can collapse. And so we're doing a study to identify cybersecurity threats and how to mitigate that. And also we recently granted a project from the DOE to study battery end of life recycling. Before the battery can be recycled, we need to de-energize the battery. We can't really de-energize the battery, so it's kind of a problem. But unfortunately, this current project is still on hold, so we are hoping to get the project started. And after this, we're also doing some research on second life battery. So when battery retire from EVs or airplanes, for example, they are not really ready for recycling because they can still produce quite a amount of power and energy we can use for something else. Professor Xiaofan also doing some research on this topic. So we have done this for a couple of years, and what we did is we did a laboratory study and we did a demonstration, like deployment. So we're trying to see how these batteries can be used, whether it makes sense economically. And then we also, so in order to understand how it make, whether it's going to make sense. So when we did another system design using new battery, so that we can have a fair comparison between what we have used battery and new battery. And this system, but unfortunately, it took us so long, even for new battery, to get a permit to install the battery. We started this one last year, so it's almost 1 year. So we're hoping to get our permit like next week, and then we'll have to go out to meet the construction, take many months, and so it takes about a year and a half, 2 years to get this system up and running. So it's really a pity that we cannot do. But the good thing, of course, once we have the system up, we can compare with our second life battery. We can compare the operating, the safety, the advantages, the performance, all kinds of things. Yeah. Actually, the one more thing we can do is in the process of developing the second life battery, we develop an energy management system. And I told my student that we want to make it universal so that we can use that to control our new battery as well. So we're going to validate our EMS software within this new system. So this is how the system look like. And you can real time, you can see the outflow, and you can see the status of each battery pack, whether you are used, and you can optimize the operation of the system so that it can help you save more money for the same amount of electricity you use. And then, on your cell phone, you can see the real-time power flow and the status. If something happens, you can press emergency button, system will stop and decouple from the grid. And then finally, we also did some recycling study. So working with the company called Queensland Manage, we have developed this plasma-based purification process. We can recycle the cathode anode material from batteries so that hopefully we're hoping that this process will produce new material that is cheaper than producing new material. I say hopefully because the recycling process itself, not just the last step of purifying, but also including the battery, like disassembly from a vehicle and transportation, storage, de-energizing, and disassembling to get the metal, like aluminum, steel, couple of plastic, and get rid of electrolyte. This huge process involved. So therefore, it may or may not be. We don't know yet. So it's something that was actually working. These are the books that we have published in the past. And with that, I think I just want to thank my students and also the sponsors for research. And yeah, thank you all. Thank you.
Like, how did the flight dynamics change when the weight of the airplane's constant? This is like the Boeing that loses more than half its weight by the end of the flight.
Yeah, that's a good question. We have colleagues from UCSD studying the flight dynamics. That does they have to like you I mean basically when you use the energy, the weight doesn't change by the vehicle. So the battery is still there, the weight is still there, the energy is gone. The weight changes negligible. But when you have battery so heavy, you have to design, you have to decide where to put the battery. You have the center of gravity is somewhere and it's easy to take off and you don't kill the airplane, let's say, because we also consider where the passenger seats, the cargo, this kind of.
And like my sister and I once were on a flight and like the batteries expanded. They were like old phones, but I don't know why that was, but like you think something like that would happen in an airplane. Like I don't know if it's a function of altitude that causes that. Okay.
We'll share a bunch of eVTOLs which are commercially available. I'm not sure if I missed this, but what's the altitude these guys go in comparison to the existing, let's say, helicopters or like?
They fly similar to helicopters. They're not flying really high. They don't fly 30,000 feet. They're flying probably around 10,000 feet.
Right.
Yeah.
Question about how the different, like for the multi-propeller type, how it's managed, like switching between like the different types of propellers. Like I would imagine if you turn off a certain propeller like mid-flight, it would cause some drag or something. So like,
Yeah.
is it that it's still like going at a slower speed or?
Most of the time they change the speed of the propeller. We start turning them off. Yeah. But if you have propellers for both takeoff and cruising,
Right.
so they only turn on the propeller for takeoff. And others will be
Right.
yeah. And once it's in air, they switch.
Right.
But do you think that battery manufacturers are going to be able to keep up in the following years with the demands for the energy density that you just spoke?
Unfortunately, no. The thing that battery manufacturers, yes, they do a lot of research, but the innovation, I would say, especially the transformational technology, often happens at university and maybe some research institutions. So this is a long road to work on. I think and we don't know whether we're going to get there.
Question. First question. Mentioned the rules don't need to use color to take off and landing, but when they fly in the sky, they just like fly as a fixed way.
Yeah.
How are they able to implement this?
Why?
I mean, does all the eVTOLs?
No. It's a different design philosophy. They sometimes they do so-called shoot wings, so they would like do this, and then they do like the wings would change direction
So
during takeoff and during push.
so that means that eVTOL use power all the
Yes and no. If your design have separate propellers for takeoff and landing, and which means some propellers will be stationary during takeoff. But if you have the two plane, I mean, because they use the same for takeoff and cruising, yes, they run all the time.
Second question, from my understanding, it looks like, the bottleneck of the motor is battery.
These are battery.
So it's.
So we were kind of making a comparison about the aircraft battery and the car battery.
Yeah.
I think that like the environment in the aircraft is kind of a lot different than from on the
Yeah,
ground.
right.
So when you're designing a battery, is there any special design considerations?
Yes.
Or if you have to put it in the air versus the ground?
Oh, of course, yes. Well, first of all, the temperature is very different. On the ground, the temperature is, well, you're still like, in the Midwest, it goes very, very cold, but in the airplane, it's always cold in the air. Secondly, when the pressure is different, high altitude, so there's like the discharge of the insulation breakdown of the connections, they're very different. Other than that, I think that there may be other issues, but I was not involved in actual aircraft design, our chief, where other people design the better pads, so we don't consider a lot. Constraints.
Right, I have some safety concerns about the electric airplane. So for the normal plane that you consume fuel,
Yeah.
and if you want to make it again, let's say emergency landing, you have to hover around, make sure all the fuel are gone. So
Yeah,
the
right.
weight of plane quite light, so you can land safely.
Yeah.
But seems like for the battery powered airplane, the weight is constant. You always carry this fuel weight during takeoff and landing.
Right.
And especially if you land, the turbulence may shock the battery cells, right? May catch fire or something. So do you think there's a safety where it's possible to commercialize for long distance, like battery powered in the future?
Well, I mean, you're right. However, there's one difference, just like earlier we discussed about, is that, traditional jet airplane, you have fuel. So when you add all the fuel to the airplane, you can take off, but you cannot land.
Yes.
It did not land, not just because of safety, but also because of weight. But in an electrical airplane, the weight doesn't change. Even though you charge them, yeah, the energy is there, but it doesn't change weight, right? So your airplane has to be designed so that it can take off and land with the same weight. So that's one thing you have to consider. But of course, there is also a competition with the landing. If it costs, say, in the case of emergency landing, where it's going to cost like extreme vibrations or shock, that can cost. But I mean, yes, I mean, you would have to, from a design perspective, you have to consider all those constraints.
Yeah, so for me, I think the huge challenge is to carry the fuel in the low land.
Mhm.
Especially in a huge shock. When you land the plane, battery cell are also like one.
Mhm. Yeah, I understand. Anything else?
Okay, let's get another round of applause.
If any of you is interested in cell electrical or study of motors, let me know. Okay.
We can have a platform. That's me.
You guys want to go over the video? What do you guys want to do? Because I have about 30 minutes between now and the next class. I really. Not making there, like very.